mantle dynamics.
Thanks very much. So hello to those of you here and also those of you online. If anyone online is in the team and I say something a bit naive, forgive me in advance, because I am going to cover a wide range of things. But anyway, it's about the mantle, where I haven't done any field work because you can't. So instead, we try to understand the mantle through using large-scale seismic information. That's one of the key ways that we try to understand it. So never mind the small text there, it's just what was sent in the abstract. So I'm going to just tell you what the Earth looks like a bit, and then why there are problems with our understanding of it, and then how my previous research might put some new twists on how we try to explain those problems. So that's what we're going to do. So, all right, here's the background. There's the Earth. So I could just list all day the questions that we have about the mantle, and the convection in the mantle drives plate tectonics. So that doesn't take any selling as an important idea. We'd like to know how well mixed it is. We'd like to know how mantle dynamics has shaped the Earth as we see it today. But obviously those questions are very general. So let's home in on some key features of what we know about the mantle. And we know that it's layered. And the reason we know this is basically from seismic wave information. So the different colors there, the yellow and the orange and the red, basically have different seismic wave speeds because they have different densities. Okay, and the contacts are drawn as sharp lines. Well, they're not quite as sharp as they might be in reality, but they're quite noticeable in from the seismic information that we have there. So, and they appear to be subhorizontal. There's one at 410 kilometers. Now, ironically, we call it D410, but it isn't always at 410. So actually, the focus of trying to really interpret these discontinuities is why they're not always at one depth. Okay. So then there's a zone called the transition zone, which is the orange color. And then we have another one, another discontinuity at D660 there. And that marks then the top of the lower mantle. So why might we have a layered density structure? Well, if you were to start from scratch, you might imagine there's a number of explanations. But because we think material is moving up and down in the Earth, we think to a very first approximation, it's not due to chemical differences. So in that case, the primary explanation is density differences due to different minerals, not different composition of the rock as a whole, but different minerals. So that means it is center stage in trying to understand mantle dynamics, to understand the controls on mineralogy. Now, I teach metamorphic geology. In the mantle, it's normally called mineral physics. It's the same subject, trying to understand what controls minerals in rocks. It's the same subject, whether it's in a green schist facies rock in Scotland or halfway down through the transition zone. Okay, the methods you use to determine those controls are different, but the ideas are the same. Okay, so let's look at what controls stuff. My phase diagram here is obviously an everyday material, H2O. So it's more general than minerals. So ice is a mineral at the low temperature side. Water and steam obviously aren't. But basically, the first thing we need to remind ourselves of is perfectly obvious, that temperature has a control on the phases that you get for a particular chemistry. Well, I suppose the reason we're used to thinking about that, especially for water, is we experience all that, but we're at one atmosphere. So we do not in our everyday life experience much of a pressure change. But inside the Earth, the pressure variations are absolutely enormous. So we have to add an axis to this graph. And even for water, it proves very instructive to do that. So it's going to look like that. Now, basically, you can see that there is a temperature dependence on when things change into each other, but there's a pressure dependence as well. So generally, lines on these sorts of diagrams are not horizontal or vertical. If they were vertical, it would mean that pressure had no effect whatsoever. And if they were horizontal, it means the temperature had no effect whatsoever. And basically, they always have some effect. Now, there's a very simple feature of these diagrams, which is always true. It's rigorously true. That if you cross one of these lines going up pressure, you always get a denser material. So if you go up from steam to water, water's a lot denser than steam. It's perfectly obvious. And that's why water is on the high pressure side. What's a little bit unusual about water, but makes this phase diagram very instructive, is that ice is less dense than water. That's actually a bit unusual. Solids are usually denser than their corresponding liquids, but not for this one. And so you can see then water is denser than ice, and that's why you can make ice melt by taking it up pressure. But these principles are very general, and they help us to understand solid relationships within the Earth. So although we've got vapor and water there, we're going to now look at solids, but it's the same idea. So pressure has an effect. Well, why does it matter? So here's well, it's not every day unless you're very rich, but it's a nice example of a solid reaction induced by pressure. First of all, we better define pressure. And trust me, that it is a word. I made a list of the different ways in which it's used in science, and it was more than 10 different ways. So actually, you've got to be a bit careful. But basically, it's a force per unit area. And if it's acting equally in all directions, like it is in this room, in the air, we can call it a pressure. And it definitely controls mineral stability. So in this diagram, we've got pressure up the y-axis, and we can take a lump of dirty old graphite and turn it into diamond by taking it to 4 gigapascals or so. And it's temperature dependent. So let's just, and again, diamond is denser than graphite because that part of the diagram, that rule always applies. 4 gigapascals is something like 120, 130 kilometers down. So you can draw a depth axis on that diagram if you want, but as I'll show by the end of this talk, you need to take a lot of care with that. So that's still a simple reaction. It's not the main one, and it's not important volumetrically in the mantle because the mantle is mainly silicates. Most people argue that the mantle, to a very crude first approximation, is the same chemistry as olivine. It isn't, but it's a lot to do with olivine. So we will work with that throughout most of this talk. So the next diagram is going to show, it's going to be a bit more busy, but it's going to show what olivine does under pressures, under mantle pressures. And it looks like that. So the lines just mean the same thing as they did before, but there are more of them. So if you go up pressure here, you see olivine turns into a mineral called wadsleyite. By the way, this is magnesium olivine. And then it turns into ringwoodite, depending on temperature. And eventually it turns into a mixture of 2 minerals, bridgmanite and periclase, and that's the lower mantle. So the bit I've colored orange there is physically what we think is the transition zone. So D410, nominal, D410 isn't always at 410. It's here, it's controlled by that reaction line. And D660 is controlled by this reaction line, although even just looking at that picture, you can imagine there is room for debate about there's more than one reaction involved, isn't there? So I am actually simplifying what some of the debates are. But the main thing is that these 2 major lines are both sloping, and so there is a temperature dependence. And what this means is, as Zanny Kotar has pointed out, that actually you can use the positions as discontinuities as thermometers. If you're lucky, if you make a list of assumptions, you can do that. So if you imagine you've got a subducting slab, so it's cold. So the first reaction should happen at shallower depths, lower pressures, and the second reaction should happen at deeper depths, that's higher pressures. So you should have a thick transition zone. On the other hand, simply looking at one of the other dashed lines, if you look at this dashed line, if it's a plume, so where we're upwelling, then, okay, well, let's do it from the plume's point of view. It's quite hot, so the D660 reaction should happen at shallower depths than usual, and then the D410 should happen at deeper depths. Do you see that means the mantle transition zone should be narrower when it's hot? And to fast forward a bit, these depth differences are measurable now. with modern seismology. So we're having a discussion here that involves quantities that can be measured. Okay, so let's look at that with a nice cartoon. So just to reiterate what I just said there, we've got a cold slab. D410 should be shallower than usual, and D410, D660 should be deeper. Hot upwelling, this should be higher than usual, that one should be lower, and so the transition zone should be narrower. Okay, so in a way then, if you can get both of these discontinuities, you should expect to see some variation in thickness in the transition zone, and you should actually expect to see the two positions correlate with each other. You know, if one is further down, the other one should be further up. Yeah, the diagrams say it better than my words can. So, and that idea has huge mileage, and there's a great deal of evidence that the temperature variations do have a major effect on the positions of these discontinuities. So I could show you places where that idea seems to work, but there's so many seismological studies now where you can't explain everything just with temperature, right? There is a kind of menu of explanations. I would put it like that. It's a menu of explanations. But what I'm going to do is just show you 3 problems. I can fish out plenty more from the literature. And in every case, of course, the studies have tried to explain it one way or another. But let me just show you 3, just to give you a flavor of it. So here's Iceland. Iceland is hot. We know because that red liquid stuff squirts out all the time. Lava, that's what it is. So we know there's a hot plume there. And so everything's hotter than it normal. What that means, if you look at the right-hand diagram, the narrow black lines indicate where we predict the discontinuities to be offset. But the map from Jenny Jenkins, who used to be here, some of you might remember her, shows that D660 is deeper than usual. Well, actually, it's going, you can see the scale bar there. It's going down to 690, something like that. So it should be shallower according to the temperature argument, but it's deeper. I think the 410 is okay. It's deeper than it should be. But anyway, the point is that's got the wrong sign by to the tune of 20 or 30 kilometers. And that kind of depth variation really matters now. It's measurable and it matters in terms of explaining how the mantle works. So let's look at another one now. And in a minute, I'll give you a potential explanation for this. So there is an explanation that Zanny has offered in this case. This is from Kotar and Deuss. So we're beneath Europe now. Can you see this is a map of D660? And the blue bits are deeper than normal. Now, we think there are subducted slabs down there. So they should be deeper than normal. Okay, so that's all right, kind of. But the trouble is that these things, the blue color is showing that they're like 30 or more than 30 kilometers deeper. In fact, it goes down to about 700. So that's 40 kilometers deeper than usual. It's more than you'd predict. And now you can imagine at this stage, you start digging into the details of the phase diagram. Yeah, this diagram showing where mineral stabilities are. So it turns out, I'm not going to go into detail on this. There's a mineral called akimotoite, which could form if the slab is particularly cold. And the akimotoite could serve to modify the normal mineral reactions that happen at that depth. Okay, so here is that story. If you imagine, here we are in this subduction geotherm. We're going through this ringwoodite stability field, and then do you see these are things called stability fields, these areas on the diagram. We're turning into akimotoite, and that means that this line here, where it takes us into the lower mantle, might be offset. Now, I'm not going to say much more about that other than to say it is a possible explanation. It's Annie's favored explanation, and you can see there is the diagram indicating this mineral there. But actually, if you look at this phase diagram, this particular one, you could argue from this diagram, which is not the only one on offer, that the offset wouldn't be huge. And so it's a possible explanation, but I'm just pointing out that these things always can be looked at from different angles. And that's what we're going to be doing. So we've got a third example now. Now this one is from South America. Now I've not shown you the map, but basically we're out in the Pacific Ocean here. There's the East Pacific rise. Then we've got some subduction position here beneath the Andes. And I've just realized I can't remember what that orange bar is. But anyway, the point is that these blue things mark where the slab should be. Now, remember, the slab is cold. There's no doubt the subduction beneath the Andes. It's a no-brainer. We know that's happening. But the slab is colder, so the D410 should be higher. It should be up here somewhere, and the D660 should be lower. But if you look at the D410, it's not obviously higher at all. And without me trying to explain all this, but remember, I'm not a seismologist, just let me quote a phrase from that paper. Detailed maps of the phase boundary topography, so they're using them, they're actually emphasizing it must be a mineral transition. It reveals deep discontinuities inconsistent with purely isochemical olivine phase transformation. So they themselves are using the word inconsistent. And what you then find is one has to reach out for other explanations. Now, the next slide I'm going to show you is a sketch of what might be happening with question marks. So it's a sketch from the same paper. And basically, they're saying, right, what we've got is some complexity due to water, not liquid water as big like buckets of water, but water kind of incorporated into the mineral structure, which modifies the mineral properties and modifies the reaction transfer, the reaction positions. They're also then postulating partial melt question mark. Okay, so trying to explain what they're seeing. And then down here, they're postulating ilmenite question mark. What they actually mean is not ilmenite, but a mineral. It's the akimotoite again. It's that same mineral. And they're saying, well, maybe some of that's down there. So the state of play now in this part of my talk is you can explain what you see if you dial up a menu of possibilities. And when you've got anomalous discontinuities, there might be unusual reactions or less usual reactions. You can appeal to varying chemistry. You can stir some water in. And there's no doubt there is water in the mantle, H2O in the mantle, and there's no doubt it plays a huge role, okay? But you can then, it gives you flexibility in interpreting the models. Then you can say, well, it's not just all peridotite down there. There might be basaltic compositions as well. So, and that, again, my role here is not to say any of these are wrong, but my role is to say you end up with quite a varied model of the mantle. It's got a bit of water here, a bit of basaltic composition there, and so on and so forth, a bit of melt here. So what we're doing actually is saying, we add to that list. Now, adding to the list doesn't necessarily make life, it doesn't necessarily solve the problems, but it might reveal a number of instances in which there's a simpler way to explain what you see. And I think what the two things that I'm going to discuss now in the rest of the talk is things that I think people are aware of, but they haven't been given emphasis in terms of possible explanatory power. So there are two things. Let's do them in that order. So there's a thing called dynamic pressure. Now, I said to you earlier that the word pressure, you have to be really careful with it. It's used in so many different ways. But we'll do that one first. So we'll do dynamic pressure first. Now, to understand dynamic pressure, you've got to realize that the Earth isn't under pressure inside, it's under stress. And what all that means is the force per unit area is different in different directions. And you don't have to look very far around you to see systems under stress. A system not under stress is the air. We are under 1 atmosphere. Sorry, people on Zoom, I'm just gesticulating with my fingers here. You can't see it maybe, or can they? It doesn't matter. You'll have to imagine me pointing in different directions and the force per unit area is the same, okay? On the other hand, if you look at the walls of the building, they're under stress because sideways, they're supporting 1 atmosphere of force per unit area, but vertically, they're supporting the weight of the building, and therefore that building is under stress. And most structures, man-made structures are, and most rocks are in a dynamic system. They're under stress. So, okay, how do we use the word pressure? One of the take-home messages from this is under certain circumstances, you have to be really careful what the word pressure is being used for, because two people will use the word pressure and mean different things. So, if you bury something in the earth, as every undergraduate has been taught, the pressure due to burial, if it's a nice calm system with no geodynamics going on, it's just like it would be if you were scuba diving. It's rho density times acceleration due to gravity times depth. That's our benchmark for what the inside of the earth has in terms of pressure. And it's a pretty good benchmark. I mean, that's the first approximation true, okay? But because the mantle is actually churning around and convecting, what that means is it's under stress. The shear stress, fluids moving, bits of fluid are moving past each other. Sorry, bits of solid rock that behave like fluid moving past each other. And so there's shear stress everywhere. Now the rock has no idea how far beneath the surface it is. For all it knows, it could be in a high pressure apparatus and it's experiencing stress. It's not experiencing burial depth. Burial depth is not a thing that you can sense directly in any regard at all. So what we have to do is step back from that and say, okay, what should we do? And this is a mighty can of worms, by the way, but I'm going to tell you it anyway. All right, let's just average the three stresses. We want one number, we'll average the three stresses. The mean stress or the average stress. Now you might find that that's the same as the lithostatic pressure, the pressure due to weight of rock. But again, as things are churning around, in general, you will find, and I can show you an example, that the dynamic pressure, the difference is non-zero. So what that means is we're interpreting the mineralogy in terms of pressure, which we then interpret it in terms of burial depth. That might not be true. There might be an extra term, the dynamic pressure. Is that a really abstruse, esoteric concept? No, it is not. It's an everyday concept. Look at this. If you fly in an aeroplane, the aeroplane flies, doesn't it? It's good news. And the reason is that it's a dynamic system with the air moving. And the air moving means that all the stresses in the air, this time it's fast-moving air, or fast-moving aeroplane. So there's lots of stress in the air, and it's creating a dynamic situation in which there's an upwards pressure in the broadest sense to keep the aeroplane afloat. But if you look at the right-hand diagram, it's even more everyday. We're at sea level. We've got a weight of atmosphere above us. So we're at 1 atmosphere of pressure. No, we're not. We're at 1005 or 1016, or this was obviously Britain was having a nice day, but Central Europe was having a low pressure system there, 989. What's all that about? Well, it's because the air's moving. So this analogy is not very precise, by the way, but it's an everyday thing. The air is moving, and so the actual dynamics of the air moving mean that the pressure isn't what we'd expect for the depth we're at. We are at zero depth, right? The sea's just out there. We're at sea level. So, and yet the pressure varies in time and in space. So actually, it's not that complicated an idea. But the people that, obviously we can't measure it directly in the mantle, but the people that make mantle models on the scale of the mantle, their models implicitly have evolving stress systems. So and I've been discussing with them, can you tell me what the levels of stress and dynamic pressure are in your models? And this is, I'm quoting from more than one mantle modeler. It's not normally their primary aim. What they want to do is explore, what was it that made Africa break off from South America or something like that? And, can we now model the continents over the last 400 million years, which actually people are doing a pretty good job of these days. So they want that. They don't want to know, well, what was the stress at, 400 kilometers? But the point is, they've got the information, the outputs from the model. And here's one example. So I said to one of the project partners called René Gusmuller, he's a real expert on mantle modeling. And so he said, all right, well, I said, let's look at South America. He happened to have a model for South America, all right, for the mantle flow. And so what he did was cut a slice at 410 kilometers and look at the dynamic pressure. the dynamic pressure is not zero. In fact, I mean, this could end up being a coincidence, but it was rather interesting to notice that the dynamic pressure beneath the Andes, this is where the subduction zone would be, the subducting slab would be, because obviously it's offset because it's tilting, it's dipping. Negative dynamic pressure, minus 200. Now, that's enough to make the local pressure look lower than it is in terms of burial depth and inhibit the reaction. And that's what the seismic survey paper, the Schmer and Granero paper that I showed you a few minutes ago, they were saying, we don't know why this reaction is inhibited. Well, maybe it's dynamic pressure. That's not a huge number, but that's enough to create an effect that will be visible seismically. And it's got the right sign for what's actually been observed underneath South America. So I think it's a very general point. We want to understand dynamic pressures better, okay? And we want to understand how big they might get in the Earth. And we do plan to run generic models to get some ideas of magnitudes, but also specific models of specific areas. So it'd be very nice to understand what actually are the parameters that control this in detail. So when you've got a model that produces an output, it's a black box, isn't it? And you want some, for me, I always want a kind of narrative behind that to assist in understanding it. But the point is that dynamic pressure, how does it vary in space and time in the Earth? Well, I don't think we know. So this is going to be part of, it's a thing that I want to pursue with the people I'm working with there. All right. So what else? So remember, dynamic pressure is this mean stress. It's you add up 3 numbers and divide by 3. But now we come to an agenda that is fairly big and close to my heart, which is, okay, could we just step back from this dynamic pressure? What about stress having a direct influence on metamorphic reaction? So that's the 4th part of the talk. Oh, before I do that, even within this, sorry, I forgot one bit. Even before we do that, can we just try and take into account for a bit in our thinking that when you have a mineral reaction, the minerals, if you're changing to a denser mineral, it's going to have an effect on the stress system around you. Now, this photograph is of a mineral changing to a less dense mineral. And all it's doing is showing that that volume change is problematic, because if something's trying to get bigger, it's pushing on its surroundings, so it makes its own stress system. Now, in this case, it's fracturing. This is a lump of coesite in garnet, and it's fracturing the garnet. So it's kind of it's a nice metamorphic example of stress building up to really quite high levels. But there's a more general principle than that, that really the stress is not just imposed externally, it might be modified by the processes themselves. So the word feedback is going to pop up in a minute. So let's have a look. So again, I discussed this with Rene, and he said, okay, well, we'll build a model with the reaction of olivine to the more dense mineral, which is wattleite. And therefore, the wattleite shrinking, right? So can you imagine, you have to use your intuition. If you're shrinking, it's going to reduce the local pressure. And indeed, that's what the model shows, that the model then shows we're getting minus 600 megapascals. That's a lot, okay? You're shrinking. You're not going to make a hole, but what's going to happen is, given, well, there's a whole issue about mantle strength, but basically the material around this area will have to deform and move in upon that area to accommodate that negative volume change. Great. So we've got a model that predicts that. But hang on a minute. If we've dropped the pressure, the reaction shouldn't be happening at all. So if, in fact, if you look at that pressure there, that pressure would then predict that the reaction should be happening much deeper. But the trouble is, we've already told the model where the reaction should be happening. So you notice I use the word prescribed here. So it's not internally consistent, but no model today ever has been. So Rene and the gang of people who generate this Mantle modeling code called Aspect, they're building this sort of feedback in, right? So it's not there yet. All I'm doing now is illustrating that we need to look at the feedback more. it just hasn't been done. Okay, right. So this time we really will do stress and chemistry. Direct effects of stress. First of all, what are the stress levels that we kind of get estimates from models? Well, it might be 300 megapascals. There might be a gigapascal in the cold part of the slab at deep levels there. So we've got some kind of landscape of stress levels. We need to ask, will they make a difference? And I'll show you that they might do. So then we have to home in, suddenly we have to swap scale right down to grain scale to understand the effects of stress. So as a metamorphic geologist, we've known literally for a century and a half that stress and deformation are, deformation and reaction are linked. You just have to look at deformed rock, and usually deformation assists reaction. There's more to it than that. But if you look in experiments, you see that as well. So the grey stuff there is gypsum, and the white stuff is a mineral forming from gypsum. You'll see these are tiny shear zones. We call them shear bands. This is only like a millimeter wide, but can you see these tiny shear zones? The reaction has gone further. So somehow there's a link between the deformation and the reaction. Okay, that doesn't mean we can explain that fully in the experiment any more than we can in nature, but it's certainly it's evidence that the two things are linked. All right, so in a minute there's going to be my favorite equation. I'm not going to show you many equations, but we need one. So, all right, again, what is stress? We've done that. But the trouble now is, look at the thing on the right-hand side. We've got one axis, but we've got three numbers. Well, what are we going to do about that? Well, frankly, nobody seems sure. I mean, I have opinions, but let's look at possibilities. First of all, we could average them. And I've just spent 10 minutes talking about averaging the three stresses. What I didn't tell you is I don't think it's the whole story. It's a kind of stepping stone. So we need to be more careful, I think, about when we've got these three stresses, the general state of play, what effect is it going to have? What happens if one of the stresses puts you in the diamond stability field and another of the stresses puts you in the graphite stability field? Poor old mineral doesn't know what to do. Okay, so average the three is misleading. It is an opinion. It is not backed up by rigorous thermodynamics. Maximum sigma 1, there is some experimental evidence, and actually, I think there is some theoretical grounding that one can bring into play there. But really, the situation is far from having any general agreement at the moment. So let's look at some maths, but then we'll look at some experiments, and that'll be the sort of closing down part of this. So stress on the scale of the Earth, it's not uniform, but actually when you zoom into the scale of grains, you have to consider a whole other different scale of non-uniformity. But the good news is that basically what really matters, there's a real role for interfaces, would you believe, in rocks, that they are where all the action happens. And so that makes life a bit easier because although it's a nice colored diagram, you can kind of ignore the inside bits of the grain, but you really need to know what the stresses are at the edge. This diagram on the scale of 100 microns will help to underpin theory and experiments, which we can then upscale to 1,000 kilometers. But you cannot short circuit this scale of investigation, and we're not going to. Okay, right, so right, I'm going to show you, I'm going to show you two equations. It's an equation that works for ordinary thermodynamics where you've got pressure. And what I'm going to do is flick from that to an equation that you'll recognize matches, because if you're going to say anything about a stress system, you've got to realize that that theory has to map on to ordinary thermodynamics when the pressure is the same, the force per unit area is the same in all directions. And it's not difficult to do that. Now, I know there are some symbols there that, let me just talk you through it. P is pressure, right? So that we've done that. Ordinary pressure. V is the molar volume of some minerals, so that's easy. F, let's not worry about, it's a constant. But on the left-hand side, mu is a thing called chemical potential. And what that is, if you haven't done thermodynamics, doesn't matter. Just think of it as a kind of proxy for concentration, or even energy. That's very vague, but I'm going to say it anyway. So what it means is, right, so you can calculate everything in classical thermodynamics with this sort of equation. Right. Now, notice what I've written there. The next equation will have stress in it, but it looks the same, right? The only thing we've changed is one symbol. We've now got this normal stress. It's the normal stress is the force across a particular interface. So it looks like it's a trivial change, but it really isn't. And the reason is that when you've got a stressed rock, the normal stress on every interface is different. So that number is multi-valued. It isn't one number anymore. And to fast forward what could be a whole talk in itself, it means there's no chemical equilibrium in stress systems, which some people don't like the idea of. And I don't blame them, but I'm afraid if that equation works, that's one of the consequences. So what it means is when you're squashing a rock, different interfaces will have different chemical behaviors. You know, on one you might want diamond to turn into graphite, on another you might want graphite to turn into diamond, and so on. This won't be particularly easy to disentangle, but there are already experiments which kind of help us to see whether this applies in practice. So I'm going to show you 3, and then I think, yes, that will be enough to kind of give you some idea of state of play. So first of all, let's turn some quartz into coesite. So Bettina Richter did this study, very interesting study, where she basically put some quartz under stress and tried to decide, I'll tell you the hypothesis in advance, try to decide whether it was the mean stress that controlled how the coesite formed, or was it one of the applied stresses, a specific one. So this is what she did. First of all, these 2 graphs are the same data. And you need to anchor yourselves in this line, which is the normal transformation line that would apply for quartz turning into coesite. So what she did was she said, all right, well, I'll tell you what, we'll just plot sigma 1 up that axis and see whether the actual experiments kind of make sense in terms of their relative position. And basically filled with coesite. So guess what? The coesite appears when sigma 1 is above the line, and it doesn't appear when sigma 1 is below. If instead you choose the mean stress, you'll see that the mean stress doesn't let you explain the appearance of coesite. So this is a clue from an experiment. Well, several clues, because look, there's about 15 experiments there. That it's to do with normal stress. It's not to do with mean stress. And about another 6 slides in advance ahead, I'll just tell you what difference that makes to the Mantle discontinuities, right? Okay, so you can see what she wrote. In all cases, sigma 1, this maximum stress triggered the reaction. Not the burial pressure, not even the dynamic pressure, sigma 1. So we'd quite like to know more about sigma 1, and we'd like to know more about when sigma 1 triggers the reaction. All right, let's look at the second example. Right, well, that's just some maths that explains what she observed with the equation that I showed you a minute ago. The second example is an analog for what olivine does in the Mantle. And the analog is we do experiments using germanium instead of silicon, and those minerals do the same sorts of things as Mantle minerals to a first approximation, but the experiments are easier. So these people got some germanate olivine, squashed it, and it turns into spinel, which is a bit like the ringwoodite you'd get in the real Mantle. And the pictures are a bit blurred, but basically the green arrows are the maximum principal stress. So if nothing else, you can see that the stress has had an effect on the microstructure. You've got relict olivines, long and thin. You've got spinel, which is isotropic optically, so it just looks black. So the first thing to give you a clue that the stress has had some effect is just to look at the microstructure, which is always a key thing to do in any experiment. So we've got that. And then the next slide is a bit equation-y, but not very. And I've cut and pasted from the paper. The condition for what's happening is basically that they're using this sigma n. So this is this normal stress. okay? And they're rewriting it, they're using the same equation. So actually, this is a second example that's the same as the first. It appears to be confirming the same thing, but in a different mineral. Now, the third example is particularly controversial. So I used that equation again, and I said, this is what might happen in a system with several minerals. And don't worry, I'm not going to go through this in much detail at all. It's a reaction. The black arrows are showing chemicals moving. It turns out that the way in which they move affects when the reaction might happen. That's not true in ordinary thermodynamics, but this is a prediction I've made, or a fragment of a prediction. So, as in the previous slides, what we're going to do is draw a kind of benchmark line to show where we'd expect the reaction under usual circumstances. And there it is. So it's a reaction that happens at about a gigapascal with a bit of temperature dependence. Now I'm going to adjust one of the normal stresses by 50 megapascals, which isn't very much. You get an offset of about what looks like 500 megapascals there. So I'm plotting sigma 1 up the y-axis. You can see the equation there is the differential stress is 50, which is very modest, and you get a huge offset on the line. Now, this is quite odd, okay? If you pick a different reaction mechanism, the line's offset the other way. And then there's another one there for luck. It won't surprise you to hear that some people said, well, that idea can't be right, okay? And it does need testing, but it's based on the equation that actually I've spent a great deal of time looking at published experiments to say, this equation applies in all these experiments. All I'm doing is extrapolating it. So I won't say any more about that because that would take a long time. But the point I'm making in this part of the talk is stress is really important, potentially on the positions of reaction lines, okay, and therefore what happens in the mantle. So let's try and wrap that up now. So, yeah, okay, yeah, it's the same diagram again. What I'm showing there, this was more addressing the crustal community, but I was saying that, oh, hang on a minute, we think this might happen at 47 kilometers, but maybe it's at 65 or maybe it's at 30, okay? And those same numbers, we're looking at tens of kilometers variation in reaction positions. That's measurable using seismology in the mantle. Okay. So that's weird. All right, let's wrap that up. We've basically got three ideas. We might use the mean stress, even though I don't like it. Let's just play with it, see what happens. We might use the sigma 1, or we might use this more bizarre prediction again. So for polymorphic transformations, if you've got a differential stress of 600, you can just do the arithmetic. That means the mean stress will be offset by 200 because we're dividing by 3. And then we'll get an offset of about 7 kilometers or so on a D410. That's measurable. It's not huge, but it's measurable. If it turns out, as in the experiments of olivine going not to waterlite, to be fair, but to a similar mineral, if it turns out it's sigma 1, 600 will give you an offset of 20 kilometers. That's really in the range of these problems that are arising in mantle seismology. So it's got legs, that idea. That idea needs to be explored more. But that's for a polymorphic transformation. If we go into this more bizarre prediction where we've got reactions involving several minerals, the offsets might be even more. So we need to expand on that theory and expand on experiments that might test that theory. So we're getting near the end now. So basically, what I'm trying to do there is show for realistic stress levels in the mantle, we need to look at the direct effects of stress on reaction, and it might help explain anomalies in discontinuity positions. And this is a lovely diagram Sani Cotard drew for when we were interviewed about this proposal. And this is an anemometer diagram showing sorts of things I've addressed already that we will be tying them together in a kind of whizzy round thing with feedback. And so there'll be going to be experiments a lot of next generation experiments with next generation equipment. There's going to be modeling on the micro scale, the grain scale, to try to explain those experiments. We're then going to upscale all that to Mantle convection models, these things on the scale of 1,000 kilometers. And then obviously we're going to be comparing the Mantle seismology with those large scale predictions, but the whole thing is interconnected. So it doesn't necessarily spin around this way, it might spin around anyway, because as we go through the large scale studies, we might think of other experiments we need, we might revisit some of the ideas, some of the fundamental assumptions. And the whole point about this program of work is that these scales are linked. You cannot, for this purpose, the purpose of this talk is partly to say, you can't really understand Mantle seismology on the 1,000 kilometer scale unless you understand reaction kinetics on the grain scale. Okay, so you need to kind of, in terms of the work pattern, you need to build in feedbacks between those ideas. And in terms of the actual mathematical modeling, you're going to have feedbacks as well. So I think there's 2 more slides. The next slide is just to say these ideas are relevant beyond the Mantle, because the Mantle is just another metamorphic rock, really. So a few years ago, there were a bunch of people that just said, what's the state of play in metamorphic geology? What are the really big problems? Now, I may have sent a comment in, but hundreds of people will have, and they came up with this diagram, right? Views on metamorphic geology. This was for their 2019 Centennial Symposium. Now, there were some words in the middle. The only thing I've changed is to make the words appear, but they weren't put there by me. You can see there's various things about dating rocks and all that, which is all very good. That's what they had in the middle. That's what they had in the middle. That's for crustal rocks. We need to understand stress and thermodynamics, stress and kinetics. That you see those 2 questions are linked. So basically, although in the project we're doing, we're addressing the Mantle, this is completely generic. This is not even just geology. If you want to understand chemistry of stress systems, it's relevant for lithium batteries, and it's relevant for whether this building rots and falls down, which I hope it doesn't, and so on and so forth. So basically, then I've given you a flavor of the sorts of ideas we've been discussing, how it relates to work I've done in the past, how it relates to the work the rest of the team have done in the past. And my conclusions then are something like that. So potentially significant effects of dynamic pressure, potentially significant direct effects of stress on discontinuities. The 3rd bullet is what we're going to be doing. And my hobby horse is this interaction of stress and chemistry. It goes beyond geology. It doesn't even just stop at the Mantle. It goes to other planets and metals and concrete and frost heave and any number of things. Thank you for your attention. So for the Zoom audience, the question is, are the effects of stress missing from Mantle models? Yes. Secondly, is it likely to have an effect to make it easier or more difficult to pass through these density contrasts, which are density filters? I've added that word, Andy. And the answer is, honestly, I don't know. We'll only find out by trying it, even with simple approximations to what the kinetics might be. But yeah, even the effects, even the, let's call it ordinary effects of pressure on mineral reaction in Mantle models are not fully incorporated because the feedback is difficult to program. Okay, so Andy is now referring to mantle avalanches, which I don't have a huge knowledge of, but he's explained that this is where in two-dimensional models, you appear to get, can I use the word catastrophic or sudden effects? Yeah, where things changed rather quickly. And then when people programmed them in 3D, the effects went away. So the answer is, I don't even have an intuition as to whether that would happen or why it happens. But what I would say is the world is obviously 3D. I'm a great fan of 2D models because otherwise a 3D model is basically a black box. And I want to understand models in 2 dimensions. You know, if you've got a fairly long subduction zone, if it's 2,000 kilometers long and I want to look at what's happening at 400, I'm going to start with a 2D model just to play around with the ideas. So I'm evading answering you, Andy, because I have no idea. But for me, part of our Mantle modeling program we will definitely start with 2D simple models. We will then move to maybe 2D real world models and eventually 3D real world models, because they're going to take the longest to run. So yeah, absolutely. I mean, you know very well how difficult it is, and I agree with you. So, so Betty's question is, how do we plan to measure the stress in experiments? And part of the answer is, we'll do some of the experiments in a synchrotron. So in the synchrotron, you can use the diffraction patterns of the individual minerals. So stress alters the lattice parameters, and the diffraction patterns allow you to measure the lattice parameters, and so you'll get some estimate of stress from that. My colleague Simon Hunt, I mean, he knows a lot more about it than me, but I think another way is you do an experiment where you include in the experiment a mineral where you think you know what it's going to do in terms of deformation for a given stress level. So you look at your actual experiment, which is doing something complicated, and you look at then your reference mineral, and you look at how that's responded to the stress level, and then you, if you've designed your geometry correctly, that will be another way to get some indication of the stress. But it's not going to be straightforward. But it, as I said, but as you, I think, I mean, Simon Hunt, the collaborators in this regard, they already have an apparatus that runs at Mantle depths. It goes to about 23 gigapascals, something like that, of confining pressure. And so he has got some, well, he's certainly got experience in attempting to estimate the stress levels under those circumstances. I do, and it's a huge question. So for Zoom people, the question is absolutely correct. Of course, that the Earth has evolved from the Hadean times onwards and is differentiating in some sense or other. Still, I'm kind of looking at Andy here. I mean, I think that's right. The core is still a bit of iron dribbling into the core, maybe. Yeah, controversial. But so your question is, I think your question is, can I address that scale of evolution? And I mean, that's just an enormous question. So I think that even though this is a big project, how it might shed new light on the overall evolution, the secular evolution on the scale of 1,000 million years, I couldn't really speculate on that. Maybe one day it would feed into a better understanding of the mantle. We hope it will, and that might help in a better understanding of the evolution. But in the Hadean, I mean, there was a huge magma ocean. I mean, that's so far away from what we're going to be addressing that I wouldn't like to comment on that. Yes, very interesting big picture. Oh, that's a really good question. So the question is, as you correctly spotted, I was talking about sigma 1, which was on the scale of the whole experiment, whereas sigma n, as one of my other diagrams showed, is on the scale of grains. And what's the difference? Well, the answer is, there could be a very long answer to that, and it does appear from the microstructure, which the authors did look at, that indeed the coesite was forming on the, for the benefit of Zoom people, I'm sorry, I've just got to wave my hands around here. But basically, the reaction was happening on the sigma 1 interfaces. And they even recorded when they dropped sigma 1, they found some reaction happening on sigma 3. So they started getting a bit of complexity. But maybe I'll just add one other thing, that in the germinate experiment, there's a wonderful microstructure there, because there, the reaction was happening on the sigma 1 interfaces, but they then evolved to be kind of finger shaped. So the stress was driving a kind of evolution, and these fingers were growing parallel to sigma 1 and still establishing the same effect on the scale of, let's say, a centimeter, but with quite a lot of complexity on the micron scale. So it's a good point. The first approximation, they seem to be tied to each other, but one does need to look at that quite carefully. Hmm. So the question is, does thermodynamics alter as a function of the stress tensor? Yes. So the question is, I've shown one equation which involves normal stress. And the question is, surely, or well, perhaps there are circumstances in which the entire stress tensor matters. And the answer is yes. If you're looking at diffusion of a chemical inside a stressed crystal, it turns out that the mathematics you use to describe that involves all three components of the stress tensor. However, those effects are what I call conceptually and mathematically second order. I think they're quite small, although there's a recent paper that says they might be quite big sometimes. But to be honest with you, that equation, although it looks simple, is for me, it's pivotal. It's kind of let's focus on that one, and then the other equations, yeah, we can maybe nibble away at them, but they're not going to be part of the main picture, probably. Thank you.